This is our second help video on 3B12, our quiz on atomic mass. We left off with problem number 1 on the front, and we'll pick up with problem number 2 on the back. In this particular atomic mass problem, they give us that there's two isotopes of rubidium, rubidium-85 and 87. They told us that rubidium-85's abundance is 72.15%, and they gave us the atomic mass of rubidium-85. It's 84.9118 AMUs. However, with rubidium-87, they knew the percent abundance. It's 27.85%, but they did not tell us the atomic mass of rubidium-87. What they did tell us, however, was the average atomic mass of rubidium. It's 85.4678. With that in mind, we can still plug our numbers in. We know the atomic mass. The average atomic mass depends on the abundance of rubidium-85 and its mass. That goes in the first, underneath the first brackets, rubidium-85. And it depends on rubidium-87's abundance and mass. They gave us the abundance of rubidium-87. We can plug that in, but we don't know the mass of rubidium-87. So some people can use an X or some letter to represent rubidium-87. I just like to use rubidium-87 symbol. So just the same way we set a problem up like this, instead of having the atomic mass, which would go right here, we plugged in the symbol. Right there, we plugged in the symbol. Remember to convert the percents back to decimal form by dividing it by 100 or sliding the decimal 2 to the left. So 27.85% becomes 0.2785. That's the contribution of rubidium-87. Rubidium-85, its atomic mass is 84.9118. It goes right here. Its abundance converted back to decimal form by sliding it 2 to the left is 0.7215. But we also know the average atomic mass of rubidium. It's 85.4678. So we can plug that in here on the left. And now we're going to merely use algebra to solve for this unknown. Again, you can put an X in there or some other symbol, but we're solving for the atomic mass of rubidium-87. First, we can resolve easily what's inside the brackets right here. The rubidium-85 by taking 0.7215 times 84.9118, and we get 61.2638637. Don't round in the middle of the problem. You're like, why are you keeping so many digits? You don't really want to round in the middle of the problem. So now we have 85.4678 equals 61.26, etc., plus what's inside this parentheses. But we can get this off this side by subtracting it from that side. So if you're adding on this side, you could subtract this side, or some people would say merely subtract 61.2638637 from both sides. So here I'm subtracting it from this side, here I'm subtracting it from the left side. If I have 61.2638637 minus 61.2638637, that essentially cancels that out. That minus something minus itself is 0. So now what do we have? We have this thing right here. What's still in parentheses is right here on top. If I take 85.4678 minus 61.26, etc., we would get 24.2039363. So how do we get rid of the 2785? Well, if you are multiplying, we can undo that by dividing 0.2785 from both sides. That 2785 will cancel out with that 0.2785. 24.2039363 divided by 0.2785 is our answer for the problem. 86.91 is the mass of the rubidium-87 isotope atom. And now for our final problem. And this one is a nice little challenge problem because we have not done one like this. So this is more of a test of your math ability than it is perhaps your science ability. In this problem, they tell us europium has two isotopes, 151, who has a mass of 150.919, and europium-153, which has a mass of 152.919. 921 AMUs. So we know the mass of both of those isotopes. We can plug those masses right into our equation for finding atomic mass. And now they tell us the average atomic mass of europium is 151.964. So they gave us the average atomic mass. That goes right here on the left side. However, what they didn't tell us were the percent abundance of 151 and 153. We don't know what the abundance is of 151, which would normally go there in decimal form. And we don't know the abundance of 153, which would normally go here in decimal form. What do we know? That there's two isotopes only. And that those two isotopes, the percent of those two isotopes together, should equal 100%. If you only have two isotopes, the percentage of 151 and 153 has to add up to 100%. But we don't do this in percent. We want to convert that 100% back to a decimal by sliding it 2 to the left or dividing 100 by 100, because when you put something in percent, you're essentially multiplying by 100. So to get it out of percent, you divide by 100 or move it 2 to the left. So the decimal contribution of 151 and the abundance in decimal form of 153 should add up to 1. So what we're going to do is let X equal europium 151's contribution. If X is europium 151's contribution, then 1 minus X would be 153's contribution. So now we can plug those into the equation. The abundance of 151 is X. The abundance of 153 is 1 minus X. So now what do? Well, we can go ahead and multiply 150.919 times X. We get this. And now we're going to take 152.921 times 1, because we're just going to multiply this through, or distribute that right through. 152.921 times 1 is 152.921. 152.921 times X is 152.921X. And there's a subtraction sign. So we just resolved what was in this parentheses and what was in this parentheses. That's all we did. Now we have 150.919X plus 152.921 minus 152.921X. We can pull those parentheses out. How do I get rid of the 152.921? Well, I could subtract that from both sides. That's what they're doing here. If I subtract 152.921 from both sides, that will get rid of it on the right side. 151.964 minus 152.921 is minus 0.957. Now we have 150.919X minus 152.921X. Since they both have X's in them, I can go ahead and subtract it. That would 151.919 minus 152.921 is minus 0.2002X. I'm looking for X. X will give me the abundance of europium 151. So how do I get rid of the minus 0.2002? I can divide that from both sides. So there it is being divided from the right side. I divide it from the left side. I have a minus on top and a minus on the bottom, so those cancel out. And I now know the abundance of 151 is 0.4780, and that's in decimal form. Remember, we stated up here that 1 minus X is going to be the abundance of 153. So I can take 1 minus X, 1 minus X, which is 0.470, and that gives me 5220. 5220 and 4780 is 1. I can put those back in decimal form by multiplying each by 100. 4780, 0.4780 times 100 is 47.8%. 0.522 times 100 is 52.20%. I was able to calculate the percent abundance of each by knowing that there's two isotopes and their abundance must add up to 100% since there's only two isotopes. In other words, 100% of europium is either 151 or 153. Using that fact enabled me to calculate the abundance of each of those. Hopefully that helps on our third problem. which wraps up the 3B12 quiz.